So today we're starting our fifth chapter. It's on geometric figures. The main focus for today, though, is going to be on triangles. Let's get going. So we're starting chapter 5 today, which covers properties of geometric figures. This is going to be another quick chapter. It's only going to take us about 3 different lessons, and we'll clear through the whole thing. So the focus for today is going to be on solving for missing angle and side measures inside triangles, as well as identifying what type of a triangle you have. A lot of this will hopefully seem like review today, especially some of the more basic concepts we start at the beginning of the lesson. But some of it might, of course, be new to you as well. Now, the end goal today is to be able to apply these concepts to more advanced situations. We're going to look at an example at the end of this lesson that deals more with the level that I want you to be at by the time we're through this. Here we go. So first things first, going way back to whenever you first learned this, the Pythagorean Theorem, or Pythagorean Theorem as some people call it. In geometry, we generally use lowercase letters to represent side lengths and uppercase letters to represent angle measures. So in this picture here, of course, you see the lowercase letters are your sides and the uppercase letters are your angles. Now the Pythagorean theorem or Pythagorean theorem says that when you have a right triangle, you can predict the side lengths of the triangle using the formula a squared plus b squared equals c squared, right? So just take each of these sides, square them, and they're going to equal the hypotenuse, which is the side across from your right angle, squared. You can use this, however, if you already know 2 of the 3 side lengths. So if you know 2 side lengths, you can use it to find the third missing piece. If you only know 1 side length, however, you can't use Pythagoras' theorem. It's just not going to work. Now, the other thing we need to recall is basic trigonometric ratios. These were pretty bizarre. I think you would have learned about them for the first time in Math 10. There's 3 primary trig ratios that you can use to relate the side lengths to an angle in a triangle. So this is where you actually kind of jump the boat here and say you're not just comparing angles or just comparing sides, you're comparing angles to sides and vice versa. So sine of your angle, so if you said sine of some angle, and the angle we usually just denote with the Greek letter theta, sine of your angle is equal to the opposite side divided by the hypotenuse. Cosine of your angle is the adjacent side divided by the hypotenuse. And tan of your angle is defined as being the opposite side divided by the adjacent side. Now, the opposite and adjacent sides are relative to your chosen angle theta, right? So if you chose a different theta, you're going to have a different opposite and adjacent. Your hypotenuse always stays the same. The hypotenuse is always the longest side of your right triangle. It's the side across from your right angle. But your opposite and adjacent sides, they can switch around depending on which angle you're focusing on. Now, again, I want to really make it clear. These above trig ratios only work in right triangles. So whenever you have a right angle, if you don't have a right angle, you can't use sine, cos, and tan as you see them up here. Now, if you know what the ratio side is equal to, so in other words, if you know like the opposite over hypotenuse, or if you know what the adjacent over hypotenuse part is, like if you know it's a number over number, but you don't know your angle, you can solve for the missing angle by using something called inverse trigonometry. There's buttons on your calculator. Usually it's just located right around where sine, cos, and tan are. And they look like sine with a -1 above it, or cosine with a -1 above it. Those are used to undo a sine, cos, or tan. So for example, I'll do a more technical example in a second, but we'll say, let's say you knew sine theta equals 2/7, right? You know your opposite and your hypotenuse. This is your opposite, this is your hypotenuse, and we know it's opposite and hypotenuse because we're dealing with sine, and sine's opposite over hypotenuse, which, by the way, these are on your formula sheet, just so you know. I believe it's on the back side, but they're on your formula sheet, so you don't have to memorize them. Bottom line, coming back to this, is we know the opposite side, we know the hypotenuse. The only thing missing here is the angle. Like, how many degrees is this? Who knows, right? I wouldn't be able to tell you off the top of my head. So to find this, you have to get rid of the sine. And a lot of people think, oh, you just got to divide sine away, which I see why people think that. That's not what actually happens. In order to undo a sign, you have to take the inverse sign, sine -1. And whatever you do to one side of an equation, you have to do to the other side of the equation. So if you wanted to find theta, you would say that theta is equal to the inverse sine of 2 divided by 7. Okay? This will be a lot more clear with a more real example. Let's do one right now. So calculate the value of theta to the nearest whole degree. Cosine theta equals 8/14. Well, since we're dealing with cosine, not that it really matters in this, but since we're dealing with cosine, we know that's adjacent, and we know that's the hypotenuse, okay? That's not really going to be useful to us right now, but it's just nice to know. So if we want to find theta, we got to get rid of this cosine. So in other words, we've got to like dig this theta outside of this cosine. So like I mentioned on the last slide, you can't just divide by cosine on both sides. That would be really nice, but you can't do that. Instead, what you have to do is you have to take the inverse cosine. So inverse cosine of this side and inverse cosine of this side. Now, inverse cosine of cosine gets rid of the cosine. That was the whole plan, right? So now we're just left with, that was awful. Now we're just left with theta. And on the right-hand side, we have inverse cosine of 8 over 14. This is what you got to put in your calculator. Now, before you throw this in your calculator, please make sure that your calculator is in degree mode. I don't know why it would be set in a different mode, but you never know. There are different modes calculators can be in. We will only need degree mode in this course. You're not going to use any of those other modes. But bottom line is, though, take inverse cosine of 8 divided by 14. And what you should get if you're in degree mode is theta equals, to the nearest whole degree, 55 degrees. Right? So the angle that would make this true, the angle that would give you an adjacent side of 8 and a hypotenuse of 14, would be an angle of 55 degrees. So visually, if we drew ourselves a right triangle, there's my right angle right there, with a hypotenuse of 14, and this is our angle, and our adjacent side, which is like this side from the angle, so this side is 8. This angle, in order to make this true, where this side is 8 units long and this one is 14 units long, that angle would have to be 55 degrees exactly to get that to work. Okay, moving on. Next example, find the side length, or find the length of side W. All right, I'm reading the words all over the place. Find the length of side W. So we're looking for this, side W. Well, let's take kind of an inventory of what we got here. We've got an angle at X. So we got this angle right here, 41 degrees is X. And we know this side right here is 4.2 meters. Now, compared to this angle, I want you to think about what kind of a side length this is. Now, remember, the hypotenuse is always across from your right angle. So we know this side is our hypotenuse. So W is really our hypotenuse here. That might be useful to know. The angle, or sorry, I mean the side across from your angle, so this side directly across from your angle, that's your opposite, at least relative to this. If we were considering this our angle, then this would be the opposite side, but we're not. We're considering this our angle, so this is our opposite side. That means this one, because it's like right next to it, but it's not your hypotenuse, but it's still right next to it, that means this one's your adjacent side. The adjacent side is always the one that's the hardest one for people to identify for whatever reason. But you just got to know it's just the one that isn't the hypotenuse and it isn't the opposite side. Honestly, that's how I go about doing it. Anyway, bottom line is we want to find our hypotenuse W. We know our adjacent side. We don't know our opposite side. Let's kind of figure out what we can use here. Well, let's remember, sine, cos, and tan are our 3 trig ratios we can use. Just in case you've never heard it before, there's a way of remembering which ratio is which. Now, it is on your formula sheet, so you don't have to do this, but TOA is a way of shortening what all the trig ratios do, right? So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Since we have an adjacent side, and we are looking for a hypotenuse, the only one of our trig ratios that has adjacent and hypotenuse in it is cosine. So I can say that cosine of 41 is going to equal my adjacent side, which is 4.2, divided by my hypotenuse, which is W. Since there's only one missing thing in this entire equation, we can now solve for W. And you can solve for it just the same way you'd solve for any other missing variable, and that's by getting it all by itself. I would start by timesing by W on both sides. So if we multiply by W, it's gone over here because that gets rid of the divide, and now it appears over here. And then I would divide by cosine 41. You can divide by a full cosine 41, right? When there's a number inside cosine, you can divide that whole thing away. What you can't do is just divide the cosine piece away. You have to divide the whole cosine 41, because cosine is eating up this 41 here. You couldn't just get rid of cosine on its own. So we can divide by cosine 41, that is allowed. So W equals 4.2 divided by cosine 41. Then you can just throw that in your calculator all in one go. 4.2 divided by cosine of 41. This gives me, and you know what, I'll just round it to the nearest tenth so it matches the same rounding we had there. This gives me about 5.6, and I guess the units on that are meters. So W is 5.6 meters. One way you can always check generally that you did something correct on this is your hypotenuse should always be your longest side. And it's certainly longer than our adjacent side. So I would say this is probably a pretty accurate answer. All right, next one, calculate the measure of angle E. Notice a capital letter for an angle, it's just good practice. So we're looking for this angle right here, angle E. Well, once again, let's kind of just take stock of what we've got. If we're interested in this angle right here, notice that we know this side on the other side. That means this side is 2.8 meters. That's our opposite. We also know this side right here. Since this side is across from our right angle, we know that this is our hypotenuse. Well, once again, if we think of SOHCAHTOA, we can determine that since we have our opposite side and we have our hypotenuse, the only one that has both opposite and hypotenuse in it is sine. So we can say sine of E is equal to the opposite, which is 2.8, divided by the hypotenuse, which is 3.9. Now we want to get E all by itself. We're trying to find that measure of angle E. Well, remember from before, in order to get rid of a sine, we have to take the inverse sine of both sides. So if you take the inverse sine of both sides, sine is going to be gone. We're going to have E is equal to the inverse sine of 2.8 divided by 3.9. And then you can just throw that right in your calculator. So inverse sine of 2.8 divided by 3.9. And that's going to give me, I guess we might as well round to the nearest whole degree. This is going to give me E equals 46 degrees. So 46 degrees would be the measure of that angle in the corner there. All right, so next up, types of triangles. Triangles generally have three main properties. Just in case you're not aware, they have three sides. That's a huge shock. They are a closed figure. That's one people often forget. They need to be closed. There can't be any openings in them. And another one that's really, really important is the sum of the interior angles is 180 degrees. So if you were to add up all of the angles inside of a triangle, it would always equal 180 degrees. So there's many different types of triangles categorized by either their angle measures or by their side lengths. If you wanted to categorize them by their side lengths, there's three different ways you could categorize them. You could call them an equilateral triangle. An equilateral triangle is one that has three equal side lengths, so all the sides are the same length. There's an isosceles triangle. An isosceles just means there's two equal side lengths, and then there's one that's an outlier. And then the last one is called a scalene triangle. And a scalene triangle is just one where none of the sides are equal to each other. They're all different measurements. Now, if you wanted to do this by their angle instead, there's again three different kinds of triangles. There's an acute triangle. An acute triangle has three angles that are all under 90 degrees. So none of them are that perfect right angle. They're all less than that. Then the next one, it's the one we're most familiar with, is a right triangle. And that's where there's exactly one angle that's equal to 90 degrees. Those are the easiest ones to identify, of course, because they got a very sharp square-like corner to them. And then the last kind of triangle is called an obtuse triangle. And an obtuse triangle has one angle that's actually greater than 90 degrees. So it's something that's like, you know, bent kind of backwards a bit, right? So there's an obtuse angle inside of that makes it an obtuse triangle, okay? These are not super critical if you ask me, but I just know that your practice problems are going to be asking for you to identify certain triangles. So it's just nice to come back to something like this. All right, here's an example. It's a little bit more of a complex example where we're throwing everything all together. An asymmetrical roof, that means it's kind of lopsided, on a shed has sections that are 18 feet and 14 feet long. The roof has a rise of 6 feet. How wide is the building? Okay, so looking at our diagram, we have to figure out how wide the building is. So we're trying to find from B to D. Like we're trying to find how long that is. Well, there's two different little triangles that are going on here. Two different right triangles, I really should say. This right triangle has a side length on the bottom of a certain length from C to D. And this one has a side length along the bottom here from B to C. In order to find how wide the building is, we would have to add BC to CD. So we'd have to figure out both of those measurements and then add them together. Well, I think it's probably a little simpler just because there's more stuff going on in the right triangle here, the right triangle, I really should say, to find CD. How about instead of calling it CD, we'll just call it something a little simpler. We'll just call it X, just to make our lines a little easier. If we're looking for X, notice that we already know the other two side lengths of that triangle. We know this side length is 6 and this side is 14. Since we already know two side lengths of this triangle, we can use Pythagoras to solve for the missing side. Just remember that when you use Pythagoras, the side that's all by itself needs to be the hypotenuse. So we're going to start by saying x squared plus 6 squared is equal to the hypotenuse, which is 14 squared. This is, of course, going to become x squared plus 36, because that's 6 squared, equals 14 squared, which is 196. And then we want to get x squared by itself. So we'll minus 36 from both sides, and we'll have x squared is equal to, I believe that'd be 160. And then we have to square root that. So x is going to equal the square root of 160, which is about 12.6. So 12.6 would be our x. Now, the other thing we need to find is BC, which I'm going to call y, just to give it a different letter, right? Notice in this triangle, we once again actually know two of the side lengths. We know that this side length is 6 feet and the hypotenuse is 18. So now we just have to find y. Now, just by the picture, we can tell that y should be a little bit longer than x, but let's find out just how much wider it's going to be. So again, because y is not our hypotenuse, we can start with it. We can say y squared plus 6 squared is equal to its hypotenuse squared, which is 18 squared. This again is going to be y squared plus 6 squared is 36 equals 18 squared is 324. And then we want to bring this 36 over to the other side, so we get y squared all by itself. So y squared is therefore going to equal 324 minus 36, which is 288. And then we want to square root both sides, and that's going to give us roughly, it actually rounds up, so I'll say it's roughly 17.0, right? And as we could tell, it is certainly longer than x. X was only 12.6 long, right? Now, to answer the final question to how wide is this building, we just have to add x and y together. So 12.6 plus 17 is roughly equal to 29.6, and the units on that are feet. So 29.6 feet is how wide that building is. Now, the next part of this question says classify triangle ABC. So triangle ABC is this one. Triangle ACD, ACD is this one. And triangle ABD, ABD is the full whole thing, by their angle measure and their side length. I'm going to start with ABC. Now, for triangle ABC, by its angle measure, this one's a little simpler. By angle measures, you can see there's a right triangle in there. And since there's a right triangle in there, we can say it's a right triangle. But then as for its side length, that's a little bit more difficult. If I go back and show you the different side lengths we could have, notice that by side length, it's either all three are the same, two are the same, or none are the same at all. Well, on this triangle ABC, we were able to determine that none of the side lengths were the same. So that means this becomes a scalene triangle. Okay, now let's move on to triangle ACD. ACD is this one here right on the right. Once again, it's a right triangle because it has a right angle built into it. And also because none of the side lengths are equal to each other, it is also a scalene triangle. All right, now the last one here is triangle ABD. There we go. Triangle ABD is like the whole big thing. So in other words, like imagine the entire big thing here, okay? Now, let me ask you this. Do you think this is going to be a right triangle? Well, some people might say yes because they go, oh, well, there's a right angle inside of it. No, those right angles are like not on the actual vertices, so it is not a right triangle. Instead, I can tell by looking at this one up here at the top that it's going to be an obtuse triangle, because this triangle, even if you like turn your head, is going to be more than 90 degrees. 90 degrees would form at some other kind of angle there. How about I just erase this to make it a little bit more clear? If you kind of turn your head and think like, oh, how can I make it like a perfect square? A perfect square would occur like kind of like that in the corner. This is going to be a lot more than a perfect square up here in the corner. So in other words, we know it's going to be an obtuse triangle. And then last, in terms of its side lengths, we know this side is 18, this side is 14, and then this side was the 29.6. So none of the side lengths are the same. So once again, we have a scalene triangle when you're classifying it based on its side length. Anyway, we're done. So for practice, I want you to work on page 176 to 188. You can also start picking away at the homework assignment for chapter 5. And as always, if you have any questions, please let me know.